Yeah, well, good evening and welcome to my home office in Annapolis. And I'm going to be making a video here this evening. It's the night before our first online class on the 23rd of March. And I'm a little concerned. Hey, maybe my Comcast Wi-Fi will go down. Maybe you won't be able to get your Wi-Fi working because maybe tomorrow's a busy morning. And so I want to have a backup for everybody. When we meet together all at the same time at 9:30, we refer to that as the synchronous mode of distance learning, online learning. That's where we're all together. We can talk to each other, ask each other questions. I can write to you. I can respond to your questions. Then the asynchronous version is there's something prepared. I'll put it on my YouTube channel, and you can view it at your leisure, the video. And then, of course, that helps you do the work that you have to do, your homework, your classwork, your worksheets. And you can do both. You can be in the synchronous mode and then offline. If you didn't catch something, you can re-listen to the video again. And so that's what this is here for. I want to do three things. I want to review series and parallel in the context of circuit elements. And we were talking about capacitors before the break. And so that's what we'll be talking about for parallel and series. I want to do a problem that was a network that had both series and parallel capacitors in it. And then finally, I want to transition. We were talking about current, the motion of charge before the break. And we started talking about things that had resistance. And I want to look at those resistors, the things that had resistance, when you put them in the networks that are both series and parallel. And so that's what I want to start with. And in order to do that, I'm going to share with you my iPad screen, and that way I can draw just like I would on the whiteboard in class or the blackboard in class. It takes a second. I got to hook up with screen mirroring. Okay, and there you can see that. I can put that away now, put that away, and hopefully you can see this whiteboard screen, and I can write on it with a little device. And so I want to talk about series, as we said, and parallel. And for now, we'll be talking about capacitors. And so let's draw real quickly a circuit of series capacitors. And first, that's a battery, right? This is the plus side of the battery, and we say it has some battery voltage, which we refer to as EMF, the electromotive force. And I'm going to put a capacitor, let's call it C1, and then I hook head to tail with that capacitor, a second capacitor, call it C2, and I connect in a closed circuit loop, and we've created a series circuit of two capacitors. Okay, a couple things you should recognize. When the current or the charge, because current is just the rate at which charge is moving, when that charge or that current leaves the battery, okay, it has no place else to go but to be on C1, and then that moves charge over to C2, and then that moves charge back to the battery. And so for things that are in series, we say both charge and current are the same in a series circuit. Now, if the battery voltage is, say, maybe a 9-volt transistor battery like we used in the lab a couple weeks ago, it is absolutely false that the voltage across C1 is 9 volts and the voltage across C2 is 9 volts. In fact, what we think is that the sum of the voltages around the loop is equal to 0. So if it's a positive 9 volts across the battery, then across one of the capacitors might be 4.5 volts, and across the other might be 4.5 volts. And we would call the voltage difference across the capacitors a negative number. We'll talk about those rules in a bit. But I guess the bottom line is the voltage across C1 and the voltage across C2 seem to have to add up to the battery voltage. The voltage across C1 isn't the battery voltage, and the voltage across C2 isn't the battery voltage. Does that make sense? Because that's different in a parallel circuit. In a parallel circuit, let's put the same battery with the same electromotive force, and there's a capacitor. We'll call it C1 as well. And there's a capacitor. Should make my lines the same because that's how we draw capacitors. There's C2. And those capacitors are in parallel. They kind of form a little ladder, where a series is an arrangement of head to tail. Okay, one of the things I think we do believe in this case is the voltage across C1 is exactly equal to the voltage across C2, okay? Parallel voltages are the same. I don't have to write that, but I can just write voltage is the same in a parallel network across all elements, 9 volts, 9 volts, 9 volts. Now, and this is getting a little ahead of ourselves. We'll talk more about this when we talk about resistors and Kirchoff's rules. If there is some charge leaving the battery and it gets to that point right up there, we call it a junction or a node. I like node, it's shorter to write. Okay, the charge which leaves the battery here, okay, that's a B, has to be equal to the charge which goes to capacitor 1 and the charge which goes to capacitor 2. Okay, so conservation of charge requires it. It doesn't have any place else to go when it hits that node. The charge leaving the battery doesn't get created or destroyed, but the charge leaving the battery either goes to capacitor 1 or it goes to capacitor 2. And the sum of those two has to be the charge that left the battery. And I think hopefully you remember that if I wanted to find an equivalent capacitor, oops, don't want to go to red, an equivalent capacitor for two that are in series, well, I better take the reciprocal of each of them. Well, look at that. I went to cool green plus 1 over C2. Whereas the parallel capacitors, the equivalent capacitor, the one single capacitor that can replace the two, is just equal to the sum of the two. And such a quick little review of things we talked about before the break and before the social distancing that we're doing now. Okay, so I'm going to clear the screen. I can save any of these if you want later, but I'm hoping you're taking some notes. I want to talk about problem number 3 on worksheet 17. And if you recall, that's a 10-volt battery. Okay, and then it goes to a 0.3. That's a 0.3. Let's clean that up a little. 0.3 microfarad. Remember, micro is 10 to the minus 6th, in this case, farads. And then I'm going to 2 capacitors. One was 1 microfarad, and the other was 0.25. I'm trying to draw these like good capacitors, 0.25 microfarads. Okay, and then complete my circuit. And hopefully you realize these 2 capacitors right here, they're in parallel, and those two together as a combination are in series with the 0.3 microfarad capacitor. And so the very first thing we might do, and I don't know why I drew it like that, let's make it look like a battery that's 10 volts. Let's draw that 0.3 microfarad capacitor. And then these two can combine, and as we said, 2 capacitors that are in parallel, you just add their capacitance. So the equivalent of those two is a 1.25 microfarad capacitance. And I just added 1 microfarad and 0.25 microfarads, and I got 1.25 microfarads. So these two drawings are exactly equivalent. That's the point of an equivalent network. And now I've got, let's see, I've got 2 capacitors which are in series with each other. And so I guess if I want to find the overall equivalent network, 1 over that equivalent network would be 1 over 0.3 microfarad plus 1 over 1.25 microfarad. Now, be careful when you take this in your calculator. I've seen a lot of people, they take 1 over 0.3, 1 over 1.25, just add those and call that the result. Remember, once you've added them, now you got to take the reciprocal again. When I did that correctly, I found that the equivalent capacitance is a 2.42 microfarads. And you might practice that just to make sure you can do that calculation, because it comes over and over again in this business, like maybe on the second midterm. All right, so once I've got that, why did I do that? Well, it seems to me we have an equation, Q is equal to C times V. So if I'm trying to find the charge on a capacitor, and I know it's capacitance, I need to know what the potential is across that capacitor. And the problem is here, as we said in the series discussion, there is not 10 volts across the zero point 0.3 microfarad capacitor, and there is not 10 volts across the 1.25. It's some fraction of that. You're going to see in a second here, it comes out to be about 2 volts across one and about 8 volts across the other. We'll carry out more significant figures, but that's about what happens. The 2 and the 8 add to 10, but there's not 10 volts that I could put into this equation right here if I put 0.3 microfarads in for the capacitance if I'm trying to find the charge on the 0.3 microfarad capacitor. I can't do it. The only time that equation works is if I have a single potential, in this case, the 10 volts. I don't know why I wrote electromotive force. Why don't I write 10 volts? And I have a single capacitor here, which we just said was 2.42 microfarads. Well, now I could figure out what charge leaves the battery. Okay, so the charge leaving the battery is equal to 2.42 microfarads times 10 volts. And so that's, you know what? I just realized I made a mistake. When I went into my calculator, it wasn't 2.42, it was 2.42 times 10 to the minus 1. I didn't look all the way to the end of the register. It's 0.242 microfarads. And so right here, that should be 0.242 microfarads times 10 volts. Well, 0.242 times 10 is 2.42. I would have been off by a factor of 10 had I not caught that mistake. So good that it occurred to me. And let's see, a farad times a volt is a coulomb. That micro, the 10 to the minus 6, just stays. So it looks to me like leaving the battery here is 2.42 microcoulombs. And where does it go? Well, come back over here. Leaving the battery is the 2.42 microcoulombs. It has to go to the 0.3 microfarad capacitor. So that must also, in addition to being the charge leaving the battery, that is the charge on the 0.3 microfarad capacitor. I'm going to call it Q.3 for lack of a better name. All right, well, that's great. Since I've said that there's not 10 volts across the 0.3 microfarad capacitor, if you follow the logic so far, then the potential across the 0.3 microfarad capacitor has to be equal to, well, let's just see, solve for V in this equation right here. It looks like it's the charge divided by the capacitance. And so that would be the charge on the 0.3 microfarad capacitor and the capacitance of the 0.3 microfarad capacitor, which is of course 0.3 microfarads. So the voltage across the 0.3 microfarad capacitor is 2.42 microcoulombs divided by 0.3 microfarads. And there's the 2 micros now cancel. 10 to the minus 6, 10 to the minus 6, cancel. A coulomb divided by a farad is a volt, something just worth memorizing. And when I did that in my calculator, and let's make sure I get the right digit here, I get 8.06 volts, about 8.1 volts. And you can see that's not 10 volts. So if you use 10, you'd be wrong. Okay, great. I have to erase here now to continue on. So I'm going to erase this stuff up at the top here, the equivalent capacitance. But I want to use the same idea here to figure out what the potential is across the 1.25 microfarad capacitor, which I admit doesn't really exist. It's something that I did in my head to combine up those 1 microfarad and 0.25 microfarad capacitors. But we could still do the same thing. The voltage across the 1.25 microfarad capacitor is equal to the charge on the 1.25 microfarad capacitor divided by the capacitance, which is 1.25 microfarads. And I'm not going to write that out. But let's see, they're in series, aren't they? And we said there was 2.42 microcoulombs on the 0.3. That means there's also 2.42 microcoulombs on the 1.25 microfarad capacitor. And so that means, ooh, that kind of looked blurry, 2 point, pushing too hard, I suspect, 2 point, nope, you can go away right now. I'm up in the corner, so let's get out of the corner here. Equal to 2.42 microcoulombs divided by 1.25 microfarads. Micros cancel. A coulomb divided by a farad is a volt. 2.42 divided by 1.25 turns out to be 1.94 volts. All right, so I think we've answered, if you're following along, part C here, haven't we? We've found that the voltage across the 0.3 microfarad capacitor is 8.06, and the voltage across the 1.25 microfarad capacitor is 1.94 volts. And if you look at the two and you add them up, hopefully you can see that they add up to be 10 volts. But wait a minute, that isn't the question that we were asked. We were asked to find the potential across each capacitor. The 1.25 microfarad is just an equivalent that I created. So the real question is, what's the potential across the 1 microfarad capacitor and the 0.25 microfarad capacitor? But they're in parallel. And what do we say about the potential across parallel elements? The answer is it's the same. The same what? The same 1.94 volts. So there's 1.94 volts across the 1 microfarad capacitor. There's 1.94 volts across the 0.25 microfarad capacitor. And that's useful to use because now the last question says, okay, how much charge is on each? And I'm going to leave that number right there. That's the charge that's on the 0.3 microfarad capacitor. In fact, what I think I'm going to do is I'm just going to put it down here at the bottom. I'll recopy it and then I can erase it. The charge on the 0.3 microfarad capacitor, which I'm designating Q.3 because I don't have a better name for it, is 2.42 microcoulombs. Now I can erase that because I got space to work here. All right, so we know that there's 1.94 volts across each of these two capacitors. I should probably not use the eraser function, draw those guys back in there. And so that means that the charge on the 1 microfarad capacitor is going to be equal to C times V, C for the 1 microfarad, and the voltage, which is the 1.94 volts. So that's 1 microfarad times 1.94 volts, which is equal to 1.94 microcoulombs, because a volt times a farad is a coulomb. On the other hand, the charge on the 0.25 microfarad capacitor is the capacitance of the 0.25 microfarad capacitor, 0.25 microfarads, times the voltage across the 0.25 microfarad capacitor, which is still 1.94 volts. And so this is equal to 0.25 microfarads times 1.94 volts. And when I took that to my calculator, I got 0.484 microcoulombs. And a little hard to draw. Give myself a little more room here. Get too close to the edge. 0.484 microcoulombs. And what do you notice about the sum of these two things right here? Well, I think 1.94 plus 0.484, both of those are microcoulombs. Put it in your calculator, and hopefully you can see it's It's just about 2.42 microcoulombs. So the charge does add up. The charge that left the battery, deposited itself on the zero point 0.3 microfarad capacitor, is indeed equal to the sum of the charge that went to the 0.25 microfarad capacitor, as well as the charge that went to the 1 microfarad capacitor, and everything checks in this problem. And so that's a good thing. Well, that's about it for that one. So now we want to move on to today's lesson, which is going to take those same notions of series and parallel. I'm going to stop this share here for just a second, and I'm going to share instead my PowerPoint notes. If I can find them, there they are. Share that with you. And I'm going to go away. This is what I hate about the Macs. Toolbars come up sort of at random on you. And I want to go to, I guess, the slideshow mode. Let's go to presenter view. All right. And hopefully you're seeing my picture of me, okay, up in the corner, and you're seeing my PowerPoint slides. And this is sort of a review of what we talked about earlier. Kirchoff's rules say that at a junction, the sum of all the currents, now we were talking more about charge when we were talking about capacitors, but the sum of the currents or charges entering a junction or a node, that dot I drew, must be equal to the sum of the currents or the charge per time, leaving the junction. Okay, that's one of Kirchoff's rules. And then he has a loop rule. The loop rule says that the sum of the charges in a potential around any closed path of a circuit must be 0. And that's where we said, okay, the battery produces an electromotive force of 10 volts, and that must mean that across each of the capacitor are 2 voltages, which add up to minus 10 volts. So when I get back to the battery, I'm at 0. Okay, and nope, I can't do that. Nope, not gonna let me do that. So I guess I gotta put that away, and then I can advance my slide. Maybe I gotta come over to here. Yep, I gotta come over here to do it. And here's an example of a series network. And what we're saying is if I start at D, I go up 12 volts, plus 12 volts. So I come up right to there, up to 12 volts. That's what's going on from E to A here. Okay, we're at 12 volts. When I go across the resistor in this way, I must lose potential energy. That's why the positive charge goes from here to here, because it's going from the higher potential to the lower potential. It turns out we don't have enough to, we don't want to do that calculation right now, but it goes down about 6.8 volts. And then we're at point B right here. Okay, and then the charge continues to move per time. So it's a current across the 290 volts. And we're back where we started, back at 0, and then across the battery again, up it goes, and keeps going around and around. And that's what's happening to energy, because remember, volts, potential difference, is potential energy per charge. And it's as if the charge moved down these resistors here, and then the battery is like an elevator. It takes the charge back up and lets it go through the resistor again. And that's the effect. Okay, and so if we believe this rule, we're saying that the potential difference across the battery right here, which I'm going to call AC, okay, because there's A and there's C, must be equal to, well, if I subtract off the potential AB, and the current going that way, right? That's the positive side of the battery over here. The current is going around this way, so I subtract off AB right here, the potential across AB, and then I subtract off BC right here. And then when I get back to here, that has to be 0. So in other words, the potential across the battery has to be equal to the sum of these two. I can just bring them to the other side of the equation and make that true. Okay, and that's what I've done right here. Well, you should remember Ohm's law from our pre-break discussions. Okay, and hopefully, nope, not going to work that way. I want my pen here to annotate this. Sorry, it's going to be a little rugged until I figure out how to make my pens, my annotations work. I want to be able to draw, so I thought I just hit that. Up there, it seems to be working. Okay, and I want to recall Ohm's law from before the break, that the potential across any element is the current through the element times the resistance of the element. Ohm's law from right before the break. So what I'm going to do is I'm going to take that guy and I'm going to put it right there. And the current in this series circuit, and remember the current is the same everywhere in the series circuit. We said that about series circuits, is just I times R1, where I've called this first resistor R1. I do the same thing for the other voltage, okay? And so that becomes that, and I get the current times resistor 2. As I said, the current is the same, and so I can factor it out. And so the voltage across the battery is equal to the current times the sum of the two resistors. You might not be surprised, but a little bit backwards from what we said about capacitors, two resistors in series can be replaced by a single equivalent resistance, which is the sum of those two. And so that's our rule for series resistors. I want to contrast that with the rule for series capacitors, which is that they add as reciprocals like this. And that's what we did in the previous problem. It's kind of backwards for resistors, isn't it, compared to capacitors? Okay, now that's hopefully straightforward enough. We want to move forward here. I got to put this away. And now I think I could just click on that. Yep, and I got to erase. I need my, hang on. I need my annotate back to do the erase, clear that. Clear my drawings, good to go. Put that away. And now, oops, I went too far. I have now a parallel network. I drew 3 this time. I was feeling a little energetic, I guess. And this point right up here, come on, go back. This point right up here is really a junction point, a node. I drew them like that. I could have tied them all together at a single point if I wanted to. I could have brought that guy right to there and that guy right to there. So that area I circled is a single junction. And what we said is that the current going into that junction has to be equal to the current going out of the junction. And I noticed the arrow is missing for I3 right here. Okay, but the current going in is equal to the sum of the 3 currents going out. And that's a mathematical statement right there in the box I'm drawing of Kirchoff's junction rule for 3 resistors in this case. Again, remembering that voltage is equal to current times resistance. So that must mean that the current is equal to the voltage divided by the resistance. And so I'm going to use that rule right here for the first current. That's I1 going through resistor 1. And similarly for current 2, which is the voltage divided by resistance 2. And of course, current 3, I'm running out of space to draw my arrows. That's the voltage divided by resistance 3. Now, you may ask yourself, hopefully not for long if you think about it, but why didn't I subscript the voltages? Okay, I didn't call this V1, V2 over here, and V3 for the 3 different resistors and the 3 different currents. And if you remember, we said for a network of parallel elements, the voltage is the same. And so there is no need for a subscript right here. Didn't need it, okay? Didn't need it at all. And so I didn't write it. Instead, I don't need that. I factored it out, and I'm left with this once I factor out the V. And this right here must be the equivalent resistance, right? V divided by the equivalent resistance. So apparently, 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3 for parallel resistors. Now, if you remember for capacitors, the equivalent capacitor in parallel was just the sum of the capacitances, wasn't it? So again, the rule for resistors and the rule for capacitors are kind of backwards with respect to each other. Okay, and so to me, that suggests a problem-solving strategy. And now I can go on to the next page here. Come on, I got to put this away. Sorry for the kind of little bit of awkwardness as I get used to pushing all the buttons on PowerPoint and the Zoom program. But this suggests a way to solve problems for networks of resistors, much like I did for capacitors on the first problem. And I'm going to always use the kind of rule I said, but you got to stay with it. You got to be consistent with it. a resistor transversed in the direction of assumed current. Oops, I hit the wrong button here. Assumed current, big word right there. Assumed current is a negative voltage. So in other words, if I've got a resistor and the current is going that way, at least I'm assuming the current is going that way, that must mean that the voltage here is big compared to the voltage here, which is small, okay? And so the voltage difference is a decrease. We say it's a negative voltage. On the other hand, and you may say, well, why would you ever do this? You'll see problems where you need to. If you're going around a loop and you're tracing the loop around and you find yourself going into the face of current, so charge is moving towards you, well, now you're going from small to big, and you get a positive voltage when you traverse that way. And we'll show one example here today before we quit of that, okay? A battery, if you go from its negative side, that's the small side, to the big side, as you're tracing around these loops that we're going to be talking about, that's a positive voltage. On the other hand, if you trace from the big side to the little side, from the positive to the negative, as you're tracing around the loop, that's called a negative voltage. Of course, Ohm's law applies for all resistors. V is equal to IR. And as a general rule, in fact, it's an absolute rule, you'll have to do multiple loops and as many junctions as you need to solve the problem, okay? And so you can never get away only doing loop rule, Kirchoff loop rule, that the sum of the voltages around a loop is 0. You can't just do that, say, 2 times if you have 2 unknowns. You would need to do 1 loop rule and 1 junction rule. And I'll try and explain that. If you're mathematically inclined, it becomes obvious that it's true. If not, well, we'll just have to live with it as something you have to know. All right, so let's do an example, okay? Oh, I need to clear my, 2 examples actually, but I need to come back here, I guess, and I need to clear my drawings, and then I can put this away, and I can move on to my next slide. And in this particular example, I've got a set of resistors, and if you notice, they're labeled R1, R3, and R4. The reason for that is I used to have an R2 right here, and it didn't really add anything to the problem. Not labeled on the diagram is the 3-volt battery right here, and I don't know why I didn't draw it, I just didn't. And what I want to find is the current in each resistor, and I'm actually going to do it 2 ways for you. One using the approach that I used on the capacitor problem we did at the start here, and then another using the technique that we just talked about today, where we actually use Kirchoff's rules in order to solve the problem. And so in order to do that, I'm going to swap around here to my pen tablet, and I think I have to stop sharing with you. And then I have to go, where's the, I can share down here. Okay, share here, and I'm going to use my iPhone AirPlay again. Share, it's going to take a second to set up. All right, yes, come on, come on. There it is, screen mirroring with you. That's good. Okay, put you away. Got a little bit of finger spelling right there. And let's redraw that circuit. And I've got it here so I can make sure I accurately put it on here from that last slide. As I recall, we had a 3-volt battery right here. Okay, and I had 3 resistors. The first one was, of all things, 1690 ohms. And then I had 2 resistors over here in parallel. Okay, one was 1,000 ohms. And then another was 3,000 ohms. All right, and so that's the problem we want to solve. And I guess the very first thing I got to do is find my work. There's hopefully the answer right there. Yep, there it is. Okay, and I'm going to approach this just like we did with the capacitor problem. I want to take those two guys and I want to combine it and redraw this circuit. And so I guess I want to go a 1690 ohm resistor just gets redrawn. Okay, and let's see, I need a single equivalent resistance that replaces those two. All right, I'm going to have to plop numbers here. So I'm looking for my numeric values. There we go. And so how do I find the equivalent resistance? Well, it's not a capacitor, it's a resistor. And so the equivalent here would be 1 over the 100 plus 1 over the, I'm sorry, I said 100, 1,000 plus 1 over the 3,000. Common denominator there is 3,000. So I guess that would be 4,000 over 3,000, wouldn't it? See what I mean about common denominator? I'd make that 3,000. And that would be 3. So I'm actually making a mistake here. I think it's 4 over 3,000 is the reciprocal of the equivalent resistance. So the equivalent resistance must be equal to 3,000 over 4 ohms, which, let's see, 3,000 over 2 would be 1,500, divided by 2 more would be 750 ohms is the equivalent resistance. So this guy must be 750. I inadvertently hit the screen here, 750 ohms. Okay, so now I want to go one more time, and I want to take the 3-volt battery, and I want to simplify this with a single resistor that replaces those two. Well, they're in series, and so the series resistance is add, and so I guess the equivalent overall would be 1690 ohms plus 750 ohms, which is equal to, what does that turn out to be, 2440 ohms? Does that look right? 0, 14, or bring the 1 up, 14. Yep, that looks about right. That's the single equivalent resistance, 2440 ohms. Okay, great. So now what do I have to do? Well, I think the first thing I can do is I can figure out what the current is right here. Okay, what's the current? Well, Ohm's law says that the current right there, oh, look at that, we popped over to blue, is equal to the voltage, 3 volts, divided by the resistance, 2440. 3 volts divided by 2440 ohms. And when I did that, I got 1.23 milliamps. Okay, so that must be the current right there, 1.23 milliamps. So I guess the question is now, what is the current in the 1690 ohm resistor? And the answer is 1.23 milliamps, right? It leaves the battery. It has no place else to go. It all goes through that resistor, and that's true. Now, what happens when it hits this junction right here, this node? Well, it must split. It doesn't split equally because the two resistors don't have the same value, but I think we can figure out how much it does split using the same idea that we used for the capacitor network in the earlier problem. I'm going to erase some of this because I don't think we need this anymore. But I guess the first question is, what's the potential difference across the 1690 ohm resistor? And I think the answer, we'll go in blue here, the potential across the 1690 is equal to the current 1.23 milliamps. Remember, a milli is 10 to the minus third. Go away. Times, go away. It's not going to let me write right there, is it? So let's erase and put it someplace else. The potential across this guy right here is equal to 1.23 milliamps times the resistance, 1690 ohms. And that value turns out to be 0.922 volts. And that's the voltage across the 1690. Okay, well, let's see. If the voltage across the 1690 ohm resistor is 0.922, what's the voltage across this 750 ohm, which really is the same as saying what's the voltage across both of those, because they're in parallel and they would be the same. Well, I guess the answer is can be found two ways. I can either go, well, 3 volts minus 0.922 volts minus the voltage across the 750 has to add up to be equal to, it's going to let me get into 0, right? So that must mean that the voltage across the 750 ohm resistor is equal to 3 minus 0.92, and 3 minus 0.92 is 2.88 sound? Does that sound right? If I go, oh, nope, that's not going to be right. I have it calculated here. Do I? Nope, I don't. I didn't do it this way on my work, but we can still figure it out. I just got to take the calculator real quick and go 3 minus 0.922, 2.07. That's what I was trying to think. 2.07. 2.07 volts. That's what's across either of those two. Okay, I'm going to get rid of this diagram because I don't think I need it anymore. So if I got 2.07 volts across each of these two resistors, the 1000 and the 3000, then I guess the next question I think I made a mistake here. What did I do? Yeah. This number right here, I think, is backwards. Let's hold up a little bit and let's check some numbers in my calculator rather than relying on notes, which are obviously flawed. 1.23 times 1190 is equal to, I'm sorry, times 1690. 3 times 1690 is equal to 2.07. So I got my two numbers backwards. This number right here is supposed to be 2.07. And then that means the math isn't undone. 3 minus 2.07 minus the voltage across the 750 ohm resistor has to be 0.922 volts. It looks to me like I read it wrong off my work when I did the problem. That is the potential difference across both of those two resistors. Okay, so that must mean, finishing up the problem, that the current which is going through the 1000 ohm resistor is 0.922 volts divided by 1000 ohms. Okay, and that's what's going through the 1000. Let's see. So that would be 0.922 milliamps, because a volt divided by an ohm is an amp. And the current going through the 3000 ohm resistor, that's this guy right here, would be 0.922 volts divided by 3. I left off a 0 here, 3000 ohms. And that would be 0.31 milliamps. Okay. And notice when you divide through by 1,000, that inserts a milli. Okay, so we've answered the problem, I guess. We found the current. There was 1.23 milliamps leaving the battery going through the 1690 ohm resistor. And then that splits that there was 0.92 going through the 1000 ohm resistor and 0.31 going through the 3000 ohm resistor. And I guess if you add these two together, can you see that you get exactly that number? 0.922 amps and 0.31, I'm sorry, 0.922 milliamps and 0.31 milliamps adds up to be about 1.23 milliamps. So the current leaving the battery going through the 1690 ohm resistor is exactly equal to the current splitting between the two resistors in the sense of they split as a 0.922 milliamps and a 0.31 milliamp in the other. Okay, so that answers the question. Things check, everything adds up, and we're good to go. Oh, there is one other thing I guess we could do, probably worth taking a second to do. When I figured this out right here, right, I think I could have also gone with the 1.23 milliamp times 750. And I think I should still have gotten that same number right there, the 0.92, right? You could have done it that way, as opposed to taking 3 volts minus 2.09 volts using Kirchoff's law, okay? I could have gone directly with that current and that resistance and found the voltage that way. It would have been the same number. All right, I'm going to show you another way to do the problem, though. And this way is perhaps a little more sophisticated, but it works, okay? And it does require some algebra. You've got to be able to solve multiple equations. Let's redraw the circuit. 3 volts, 1690 ohms. That's terrible. 1690 ohms. That 0 so you can see it. Okay, then you had the 1000 and the 3000 ohm resistors. And I think I had this one as the 1000 before. And this one is the 3000. Okay, and so if you do that, I think you can use Kirchhoff's rules directly. And Kirchhoff's rule says the sum of the voltages around any closed loop has to be equal to 0, and the sum of the currents going into a junction has to be equal to the sum of the currents leaving that junction. And so the first thing you have to do before you can do this problem in any way, shape, or form is you have to decide what the currents are. And so I'm going to call that current I1. If you remember from before, that was 1.23 milliamps. I'm going to call this current right here going through the 1000 ohm resistor. I'm going to call that I2. So I'm going to call it here, yep. And I'm going to call this current right here going through the 3000. I'm going to call I3. Okay, and you have to do this at the start of the problem. You might be wrong. I'm pretty sure I'm right here. This is the positive side of the battery. I think the current is going to go around clockwise through these loops, but there are some problems where it might not be so obvious if you got multiple batteries. So anyway, I think we said 2 things. The first thing we said is the junction rule. The junction rule stated mathematically is that I1 must be equal to, that's the current coming into this junction, must be equal to the sum of I2 plus I3, right? Has to be true. It's a junction rule that tells you that, okay? And now let's see, what else do we have? I can take a loop and I'll start right here and I'll go all the way around that loop right there. Can you see it? Okay, and we said that the sum of the voltage rises and drops around that loop have to be equal to 0. And so I'm going to start right here, and I'm going to go, well, I go across the battery in that direction, and so that's plus 3 volts. Okay, and then I'm going to go across this resistor right here, going that way. And we said if you go from the high side of the resistor to the low side of the resistor, the voltage is going to go down, and so I'm going to subtract off the voltage there, the unknown I1 times 1690 ohms. Okay, and then I come through here, and again, I got a voltage drop because this is the high side, that's the low side. I'm going from high voltage to a low voltage. Okay, and so I go minus I2 times 1,000 ohms. And now I'm back to where I started, so that sum must be equal to 0. Okay, one more loop, I guess. We'll do this one in black. I chose, I guess, yeah, let's do that one. Okay, let's go all the way around the outer loop. Okay, and again, we're going to start right here. We'll go all the way around, so it's 3 volts minus I 1 times 1690 ohms minus I, this time I3 times 3,000 ohms is equal to 0. Okay, great. What do I have here now? I think a mathematician would say, I have 3 unknowns. The unknowns are I1, I2, and I3. But I have 3 equations, the junction equation from Kirchoff and 2 of Kirchoff's loop equations. And a mathematician would tell me that just by working those around, I should be able to solve for what I1, I2, and I3 are, because you have 3 equations and 3 unknowns. And, it's a little tedious, but you can always solve for that. Now, a couple of people, and I mentioned this, and I just want to show you something, might have said, well, isn't there a third loop? And I'm going to make it in this green color. Oh, right here. And there is. It's right there. Okay. And I'm going to put off on the side here. I'm going to start right here, and I'm going to go around in a clockwise fashion until I come back. And let's see, that's going to be minus I3 times 3,000 ohms, right? And I'm probably going to run into my corner here again. But now remember that case where I said you're going from the low side to the high side as you get back to where you started from? So you're like a salmon going upstream into the current. And so you're going to the higher voltage. So we're going to add on I2 times 1,000 ohms. And that, because I'm in a closed loop, I'm right back at this point right here where I started. That has to be equal to 0. And I put the 0 over here on the left side. Here's something I want to show you. Let's look at a linear combination of these 2 loop equations. Okay. And I think the easiest thing to do is subtract the bottom equation from the top equation. So that's the same as changing all the signs and adding them, right? So this adds to 0. This adds to 0. And then what I'm left with is minus I2 times 1,000 plus I3 times 3,000 ohms is equal to 0, which, if you notice, is exactly that if I multiply through by -1, which just changes the signs around. So if I multiply this thing through by -1, that becomes positive. This one becomes negative, and it's exactly the same as the equation that I developed from the third loop. What a mathematician would tell you is that third equation is not linearly independent from the red and the black equation. It's just a linear combination. I added things and I got the same one. So you can't solve this problem by merely looking at the three loops that I've highlighted here. You have to have one junction equation, and then any two of the three loop equations, because in this particular circuit, there are three loops, and I've gone through each one. Okay. And so I guess the only step left is to solve these system of three equations and three unknowns. And I'm not going to do that in the interest of time here. But there are all kinds of those of you who have a TI Inspire, you could just plug these three equations into TI Inspire and solve it. Others of you might choose to use Wolfram Alpha to solve the three equations and three unknowns. And if you do, I guarantee you the solution to these is that, let's see, I1 is going to turn out to be 1.23 milliamps. I2 is going to be equal to exactly what it was before, which is 0.92 milliamps. And of course, I3 is going to be equal to 0.31 milliamps. And there's less work until you get down to the algebra of solving these three equations. If you're an equation solver, it's the easiest way. If you don't have an equation solver, it's a little bit of tedious algebra. How'd you go about it? My advice would be to substitute that in for your two I1s, okay? And then you would have two equations with only two unknowns, I2 and I3. And then I would come up with some sort of linear combination on those folks in order to either eliminate I2 or I3, okay? And then solve for the equations. All right, I think that's enough for that problem. We've solved it in two different ways. We've beaten it to death. I want to show you an example problem of why Kirchoff's loop method is absolutely necessary at times. And here's the problem I want to do. It's actually in the PowerPoint, but I'm just going to draw it right here. And I've got a 10-volt battery, because we've been using 10-volt batteries all along. And I've got a 5-ohm resistor right here. And I've got a 20-ohm resistor right here. And over here, I've got a 10-ohm resistor. And then over here, I've got a 20-volt battery. And there's my circuit, okay? Despite my bad penmanship, hopefully you can see three resistors, 5, 10, 5, 10, and 20 ohms, two batteries, 10 and 20 volts. And of course, the thing I want to do is I want to find the current in the 20 ohm resistor. All right, now here's the deal. Can anybody see a set of resistors that are either in series or parallel? People claim there are. Some people say that the 5 ohm and the 10 ohm are in series. And I would argue, no, they're not. This junction right here can't be there if they're truly in series. If they're in series, they connect head to tail with nothing else there. And then some people would try to claim that the 10 and the 20 or the 5 and the 20 are in parallel with each other. But the fact that the battery is there means that they are not individually in parallel with each other. In fact, in this circuit, there are no further simplifications possible. We've simplified it to the smallest amount. All right, so we have to solve it using that second technique we did on the previous problem. And so the very first step, always, if you're using that technique as a strategy, is you have to assume you know the direction of currents. This is why I say you might not always know, okay? I think because that's the positive side of the battery, it's going to force charge that way. Current is going to go that way as I've drawn it through the 5 ohm resistor. And I think because that's the positive side of the battery, I think the current going through the 10 ohm resistor there is going to go that direction. I'm going to call that I3. And I think that right there, I'll call it I2. I think that's the way the current is going to go. And have reason to believe that. The only thing is if this 20-volt battery was very big compared to the 10-volt battery, and I don't know if a factor of 2 is enough, it is possible that I3 may actually cause I1 to reverse direction and actually charge the 10-volt battery. It is possible that that could happen. At this point in the problem, I don't know. And that's why I use the words, you have to assume a current direction. This is my best guess at the start of the problem. We'll see if I'm right. If I'm not right with these directions, what do you think is going to happen when I solve for I1, I2, and I3? Well, if I pick the wrong direction, like perhaps I1 is actually in the other direction, when I solve the values, I think I'll get a negative number. Okay, so the big part here is writing the Kirchoff loop equations and the Kirchoff junction equations that exist. And I'm going to start with this junction right here up at the top. And what currents are going into that junction? Well, it looks to me like I1 and I3 are coming into the junction, and leaving the junction is I2. Good to go on that? The current going in has to be equal to the current going out of a junction. And by the way, what's the current right here and the current right here? Now, I think the 20-volt battery and the 10 ohm resistor, they're in series, so this must also be I3. And the 10-volt battery and the 5 ohm resistor are also in series. We said in series, current is the same, so that has to be I1. Now, if this troubles anybody, we're going to prove in the lab next Tuesday. We're not doing a lab on Tuesday the 24th, but 7 days later, a week from Tuesday, we are going to do a lab, and I'll show you this. We'll put the circuit sensors right in the circuit, and you'll see that absolutely it doesn't matter whether I measure the current here or here. They're in series; it's the same. So I guess some of you may be wondering, what about that junction there at the bottom? Well, notice coming in is I2 and going out is I1 and I3. So you get exactly the same junction equation if you use the junction at the bottom, only the roles are reversed. I2 is coming in, I1 and I3 are going out. Okay, so that's our first equation. The second thing we have to do is start picking some loops. And I'm going to go with a loop right here. I'm going to start, I always like to start right before the battery. You don't have to. So I want my first term to be a positive battery term. And I'm going to go around that loop right there till I come back. Remember we said that's plus 10 volts because I'm going from the low side to the high side. If I'm going in the direction of the assumed current, that means the side on the left here is higher than the side on the right. So voltage is going down as the current runs from left to right. So we subtract off I1 times the 5 ohms. Okay, and then I'm coming down through the 20 ohm resistor with I2. And again, I'm going from the high potential at the top to the low potential because that's what's driving the current. And so that's minus I2 times 20 ohms. It doesn't work out right. 20 ohms. And now I'm back to where I started from, where I drew my X. So that has to be equal to 0. Okay, and I have to pick another loop. I chose this one right here arbitrarily. I'm going to start right there. And it doesn't matter whether I go clockwise or counterclockwise around a loop. I'm going to go this way, because that way I'm going with the current in all cases. And so if I start right here, I first go across the battery from the low side to the high side. So that's plus 20. And then I guess I'm going to start putting a plus. That's the high side. That's the minus side. So I'm going down. That's minus I3 times 10 ohms, right? And then I guess this is the plus side. This is the minus side. I'm going down because that's the direction current's going. Minus I2 times 20 ohms again has to be equal to 0. Okay, great. I think we're good to go here in the sense of I have 3 independent equations. I have to figure out a way to solve them. I'm going to leave that either to your algebra or to you going to Wolfram Alpha. I think if you solve them, you'll find that I1 is equal to, minus 2/7 of an amp. Darn, darn, darn. I2 is equal to, Nope, I'm sorry. It came out right. Plus 2/7. And then I2 is equal to 4/7 of an amp. Okay. When I was in my TI Inspire doing this, I was in the exact mode. So it actually gave me fractions. If you're in a different Wolfram Alpha, you may get decimal form. It's okay. It doesn't matter. And I3 is equal to 6/7 of an amp, which hopefully you knew because once you saw those two, remember that oh, wait a minute. No, no, no. I'm absolutely wrong. I read my calculator wrong again. This guy right here, shoot, was a negative voltage after all. So what does that mean about my assumed current right here? Apparently it's going the other direction. Apparently 20 volts is big enough that it actually drove I1 into the battery, charging it. And now let's look. We said that I2 has to be equal to the sum of I1 plus I3, didn't we? Is that true? Is 6/7 plus a minus 2/7 equal to 4/7? And the answer is, yeah, it is. Okay. And so that further tells me that I got the wrong direction here. I1's going the other direction. But much simpler to solve if you have a nice way to find those how to solve those three equations and three unknowns. Otherwise, I admit the algebra could be a little tedious. All right, well, I think we've done enough for a day here. Actually, if you look at the schedule, what I've gone through today are both the lessons for Monday the 23rd and Wednesday the 25th. Okay, the next time you'll need to watch a video about the lecture for class will be on Friday, and hopefully we'll have figured out if Zoom is going to work for us by that point. All right, I'm going to do some things here. I'm going to stop sharing. If I was in class right now, I'd ask if there are any questions, and I would tell you it's now time to pull up. Well, let's see, what are the next two worksheet numbers? I guess it's 21 is the very next worksheet. So either pull it up on your computer or, nope, I'm wrong. The next one is, nope, it is 21 is the next one. Okay. And then on Wednesday, we'll be working 22. And there's no class on Tuesday, the 24th. I'll be making myself available for office hours during the normal lab period. And in that period of time, I expect you to work on worksheets all the way up to worksheet 20, which is the last worksheet before the break. Oh, that's I guess about it. I'm going to stop. I'm going to stop recording here, and hopefully we'll see you in a Zoom meeting here in the next day or two if this didn't work out for you for these first two lectures.